Hello physics students. So in the last video, you learned about simple harmonic motion, which was a special kind of vibration, a smooth vibration, such that the object's displacement either followed a sine or a cosine function. Today what we're going to learn is that those vibrations can actually travel through space. And when they travel through space, we call that a wave. So that's where we begin. Waves, it's a transfer of vibrations through space, but an important point to note is that waves are a transfer of energy, not matter. So for example, when you're looking at waves in an ocean, the waves are traveling from miles out to sea and they move inland. When they finally crash at the shore, what's arriving is not the water from miles out to sea. It's not like that, like a cup of water travels all the way in and gets to the shore. All that travels is the vibration, the water out to sea and the water at the beach, they stay in place. It's just that up and down motion that's traveling. Another thing that you have to know in the Regents curriculum is something called a wave pulse. Instead of waves continuously traveling one after another like in the ocean, a wave pulse is just a single disturbance instead of a continuous set of vibrations. So in the case of a wave pulse, what you do is, like if you have a tight rope, you shake the rope up and down just one time rather than continuously. So it's not simple harmonic motion, it's just up, down. And then that creates like a bell that travels, and the vibration travels, not the rope. The cord that you're holding in your hand stays there. And again, it's just that vibration. So what I'm going to do is show you a wave pulse now so you could see that indeed it's the vibration that moves, not the matter. So let me reconfigure the camera. As you can see, I've got a very long slinky stretched from one side of the screen to the other. And what I'm going to do is use this to demonstrate a wave pulse. So first, let me create a wave pulse and you could watch it, then I'll talk about what's going on. So here you see my hand, and watch what happens, and then with my hand, and then watch what happens to the spring, what it does in response. All right, so what I did is, in terms of physics, I pulled on the spring with a force in this direction, and the spring moved with a distance in this direction. When I pull with a force over a distance, that is work, which then becomes spring potential energy. The coils become stretched or elongated. Then I rapidly pull my hand back the other way with a force over a distance, and again, I'm putting in work. I put work in this way, and then I pull work this way, or put work in this way, both times stretching the spring out like this. And so that is now stored, that work as energy, and then that energy goes from one side of the spring to the other. But notice that the coil, the spring coil in my hand, does not go to the other side. All that goes to the other side is the disturbance. The coil in my hand stays in my hand. This coil right here stays right here, and again, only the energy or the disturbance travels through the spring. And if someone was at the other end holding the end of the spring, when that disturbance came down to them, they would receive a little nudge. In other words, they would get work done on them by the spring. The energy that I put into the spring would be delivered to them like that, okay? So the next thing I want to point out is that there's actually two different kinds of waves I could create on this slinky. I could do what I just did, shaking my hand side to side like this in simple harmonic motion. And then what I would not be creating, I would not be creating a pulse, I would be creating a continuous wave. So I'm going to do that, and then what I'm going to do is I'm going to freeze a frame, and then we're going to talk about what we see like if I were to snap a picture of such a wave. So again, SHM like this, and let's see what the spring looks like as a result. So what you should see is that the spring looks like either a sine or a cosine graph. When I move my hand continuously in simple harmonic motion, I'm sending, in a sense, pulse after pulse, and it makes that continuous wave. So that kind of wave, when I shake the spring side to side, and the wave motion is in the forward direction. In other words, actually, I'm shaking, in your perspective on the screen, up and down on your screen as you're viewing it. but the spring is moving from the right side of the screen to the left. So my shaking is perpendicular to the wave motion that we call a transverse wave. So again, I was going like this, and that was traveling this way. Vibration perpendicular to the wave motion. The other kind of wave that I can generate on this spring is, instead of shaking side to side like this and having the wave go like this, I'm going to shake forward and backwards, and then the wave's going to move forward. So instead of shaking perpendicular, I'm going to be shaking parallel to the wave motion. And watch what happens. First, I'll send a pulse. Okay, so that kind of wave is called a longitudinal wave. And if I shake my hand here in simple harmonic motion, what I will be doing is creating those longitudinal waves continuously. So it'll look like this. I'm going to freeze the image after I get a few waves building up. So let me go ahead and shake my hand. Okay, what you should see at this in this photograph is that there are places where the coil is packed together densely, and then there are places where the coil is stretched apart. So that's a longitudinal wave. We're going to talk about what those compressed regions are and what those stretched regions are. But let's go to the board, and we'll summarize with some diagrams as well as learn some other things about these waves. Let's summarize the two wave types that we saw on the slinky on the floor. So transverse wave is one in which the wave vibrations are perpendicular to the wave's motion. In other words, I shake the spring up and down, and then those up and down vibrations travel along the spring. So if I were to snap a photo of the spring as I was shaking the spring repeatedly, it would look something like this. This light line represents the equilibrium position of the spring, and we see there are parts that go up, parts that go down, and that travels this way. Now, just a couple points. Again, the amplitude, like we learned in the last video, is not from the whole range of motion. Like if you were in an ocean wave and you go up, and then from the peak you go down to the bottom, say 10 feet. I'll just pick a number in feet. The amplitude's not 10 feet, it's half of that from the equilibrium position outward. Then there are parts of the wave that are named, like the top of a wave. You've undoubtedly heard this when you're looking at waves in the ocean. The top of the wave is called a crest, but the bottom of the wave, a lot of people don't know, is called a trough. So that's what we call the bottom of a transverse wave. Then there's also, from crest to crest, that distance we call the wavelength. So I didn't write the word wavelength, but that's what it is, from here to here, or from the trough to the trough is also the wavelength. Now this is a Greek letter, a fancy symbol that we use to represent the wavelength, like we use A for amplitude, M for mass. Well, this is called lambda out of the Greek alphabet, and it's like this curly like symbol like that. Basically, you do your best to draw that. If you don't want to make it curly, it's perfectly acceptable to make wavelength like that, so you could write it that way. So let me create a pause, allow you to copy this stuff down. One more point. One example of a transverse wave we're going to learn about later in the topic is called, it's light, so we'll be studying light in more detail, transverse wave. All right, let me create a pause to give you a chance to copy these notes down. All right, so the other kind of wave that I talked about on the floor over there is a longitudinal wave, and the definition there is that the vibrations are parallel to the wave's motion. In other words, if this were the slinky, it's a little hard to draw. This is easier to draw, but I'm drawing the coils of the slinky. I shove the slinky forward and back, so the vibrations go like this, and then my hand goes like this, and the vibrations travel in that direction. So the parts of a longitudinal wave are compressions and rarefactions. Compression kind of makes sense when air gets compressed, you know, it gets like squeezed. So where the spring coils are squeezed together, compression. The part where they're the most stretched out, we don't call a trough, we call a rarefaction for longitudinal wave. Longitudinal waves, like all waves, have wavelength. You can measure that from the compression to compression or from rarefaction to rarefaction or any two similar points in the wave's motion. And one example of a longitudinal wave that we're going to be studying later in the topic, a whole video devoted to it, is sound. So there's an example of a longitudinal wave. So let me create a pause to give you a chance to copy these notes down. All right, so now another thing that I want to talk about is something called phase, because as you can see, this is essentially a cosine graph. And so we can label how far away on the cosine graph different points are, and we use the concept of phase to delineate how far away a particular point is from another in the cycle of a wave. So what I want to do is show you the wave again on the floor, a still of it, so then I could introduce the concept of what we call phase. So let me reconfigure the camera. So here's the image again of the transverse wave traveling down on the spring. Once again, it traces out a sine or a cosine graph. Now you can use the knowledge that you gained when you studied sine and cosine graphs in math class, particularly the knowledge about the x-axis, to specify the difference between any two points on this wave. So to show you how that's done, let's go back to the board and I'll tell you about something called phase. So here's a sketch of that still frame that you just saw. Now if you understand the x-axis of a sine or cosine graph, like when you studied them in math, then you'll have no trouble understanding what phase is. Suppose I choose to label this point A, and then this point B. Now if you were to graph the sine graph, which is what this is, on x and y axes, you would find that this peak, this crest, occurs at 90 degrees on a sine graph. So we would say the phase difference between points A and B is 90 degrees because that's how far it is along the x-axis. The phase difference from A to C, while this is 180 degrees along the x-axis of a sine graph, so the difference between A to C is 180, the difference from A to D is 270, and the difference from A to E is a full 360 degrees, which we don't say that they're 360 degree phase difference from each other. Basically, as you see, this is the same kind of point as this one, and when the phase difference is 360, we actually say that those 2 points are in phase. They're the same kind of point relative to a sine graph. But this kind of, so basically every quarter of this graph from peak to midpoint or midpoint to peak is 90 degree phase difference. But we could start with any point. Like here I start at the beginning of a sine graph, but what if I started at the trough? Well then, what is this point? Well, this is 90 degrees, and here's another 90 degrees. So from here to here is a 180 degree phase change. So I'll create a pause to give you a chance to copy these notes down. All right, another thing that we're going to study today is reflection, because waves can and do reflect when they hit things. So I'm going to show you some examples or some instances of the wave reflecting off the end of the slinky in a moment, but what I want to just say is we're going to pay attention particularly to the phase change that happens upon reflection. So give me a moment, I'll reconfigure the camera for the next set of demonstrations. So what I've done is I've moved the end of the spring so that it's now fully in view in the camera view. You could see this spring. I don't know how well you could see this, but the spring ends here, and then from here on is a string. And right now, this end of the spring is free to move. What I'm going to do is I'm going to lock it in place so that it can't move by just putting this concrete block right here. And now you see the end of the spring can't really move because the concrete block is holding it. What I'm going to do is I'm going to go to that end of the spring off view, and I'm going to send a single crest toward this barrier right here, and we're going to watch that the wave crest that goes like this bounces off of this, but there's an important subtle difference in the wave that reflects, and I want you to watch very carefully. So, hold on, let me get to the other side. All right, here we go. Again, you can't see me, but I'm going to send a crest toward that concrete block. So, here we go. All right, so what you should have seen is that when that crest struck the immovable barrier, it flipped upside down and turned into a trough. Let's take another look. Okay, so nice flip there. Very clear that we saw a crest turn into a trough. Now, in terms of what we just learned, we would call this, the difference between these two is a 180-degree phase change upon this reflection. But the next thing I'm going to do is I'm going to remove the concrete block, and now this end of the spring will be free to move again. We're going to see again that the wave reflects off the free end, even though there's nothing holding it to reflect off. With nothing there, it still reflects, but I want you again to watch the reflected wave carefully to see something else about the phase in this case. So let me get over here. Okay, again, I'm going to send a crest. Watch what reflects back. All right, you should have seen that what reflected back was a crest. It came in as a crest and it came back out as a crest. In other words, the wave did not flip over this time when the end of the slinky is free. So let's watch that again. Okay, so there it is, reflection, a crest came back a crest. And what we would say in this instance, when a crest comes back a crest, that there is no phase change. It came back the same wave. So that is reflection. Let's go back to the board and summarize what we just learned. So summarizing what we saw, if a wave approaches a fixed object like a wall, in this case a crest, when it reaches this point, it'll reflect. In other words, it'll bounce off the wall, but it will come back upside down. In other words, crest changing to trough is, as we saw in the earlier segment of notes, that's a 180-degree phase change when the wave flipped over. If we sent the trough, it would bounce back as a crest. But I just want to point out that in this case, it's hitting a wall, but technically, some of the wave does go into the other object, even a wall. So if we had detectors on this wall, when this wave hit, it detects a little bit of a vibration. So some of the wave goes into the wall. So the point is, it's not that this thing is immovable. The point is that it's less movable than this. So we could, for example, have a real thin coiled slinky, as we saw in the back of the room just now. And then the next thing was not a wall, but a slinky with thicker coils. And the same thing would happen because we'd be hitting a more rigid second, we'd say, wave medium. And so that would still flip the wave over, going from less dense to more rigid medium flips, causes the phase change. The second case we saw, this is how I chose to diagram. Imagine this is not fixed to a wall, but it's on a pole with a friction-free ring, so this can slide easily. I send the crest. When it bounces back, it comes back as a crest. The reflected wave has no phase change. If I sent a trough would bounce back. All right, so let me create a pause to give you a moment to copy these notes down. All right, I just want to point one thing out, that in how I said that the wave just has to hit a more rigid material for this phase change, same thing here. We could have a thick coiled spring and then a thin coiled spring, so some of the wave goes through and some will reflect, and the part that will reflect will have no phase change if we go from more rigid to less rigid. So anytime two mediums or things that a wave can travel through are in contact, waves can pass from one to the other, and there'll be some bit of reflection as we see here. The final thing for today, speed. Waves obviously have speed to them, as we saw them traveling down the slinky. So, but there's a relationship between speed, wavelength, and frequency. And by the way, this relationship here works for all waves. So whether you're dealing with water waves in the ocean, sound waves, light waves, this equation works for all waves, not just the waves on the spring that we studied. Now, typically, the concept here is that for a given type of wave, like light, or a given type of wave like sound, the speed of the wave generally is a fixed number, like the speed of sound. Regardless of what kind of sound, a trumpet plays, a clarinet, doesn't matter what the sound source is, it pretty much travels, all the sounds go at the same speed. What changes is, if this side equation is fixed, then that means there's an inverse relationship between wavelength and frequency. In other words, if one wave has a very long wavelength, then it'll have a very small frequency. And if another wave has a very short wavelength for the same speed, then it has a high frequency. And if you think about why that would be the case, two waves, equal speed, one with a short wavelength and one with a long wavelength, why the frequencies will have that pattern, it'll make sense, but I'll talk about it more in a future video. So today, you'll just be on the homework applying this. I'm not going to do an example because it's pretty straightforward. You're usually given 2 out of the 3 variables, and you solve for the third one. So that's just a little bit of algebra. And a reminder that waves also have period, the time it takes for, say you're a crest, you're in the ocean and you're on a wave crest. And then you're going to go into the trough and you're going to go back up to a crest. You're floating like on an inner tube. Then there's a certain amount of time that it took you to go from crest to crest. So that would be the period of the wave. And they also have frequency, how many waves pass you in a given second. And this relationship that we learned for simple harmonic motion also works for waves. So let me allow you to copy these notes down. I'll create a little pause. Okay, so that's it for today. Basic information about wave types, that a wave is a traveling bit of energy. I put in work when I shook that slinky. I pulled force times distance, and then I pushed down force times distance. And so I put work in, or energy, and then that energy went through the slinky, and on the other side, if someone was holding it, they'd receive that little bump of energy. From me, it went through the spring. But the coils of the spring did not move, only the energy. And that's true of all waves. They're never transmitting any matter. They're just transmitting vibrations. Then study the 2 kinds of waves, longitudinal and transverse waves, know all the parts of the waves, know phase and reflection, and this nice relationship. Oh, by the way, this relationship, V equals lambda times frequency, is in the waves section, so I just want to point that out. So as you could see, the top formula right there in the waves section of the reference table, which is page 5, is that V equals, well, they have frequency time wavelength, but same equation. Okay, I hope you enjoyed the video. I hope you enjoyed the physics and the demonstrations. I'll see you in the next physics video.